Hi everyone, thank you for having me. My name is Leandro Ayarde Henríquez. I'm a research fellow of the School of Physics, Trinity College, Dublin. So today I want to talk about the multiple relation between electron density symmetry and a special set of parametric polynomials called unfoldings based on the analysis of the pyrolytic transformation of Cubane along the intrinsic reaction coordinate. Well, this is the outline. I will briefly justify the reason why Cubane was targeted, and I will refer to some key aspects of BET, which is short for bonding evolution theory. I will place the idea of this correlation through Cubane's decomposition and how we gauged this to derive a bond polarity scale. And finally, a set of conclusions. So Cubane is indeed a fascinating cube made of 8 CH units, and its synthesis was a challenge for many years. And at some point it was actually considered impossible due to potential structural instabilities, until Eaton and Cole succeeded in 1964. And once it was synthesized, its exotic geometrical features rapidly captured the attention of the research community. Both its highly strained and kinetically stable structure made it quite attractive material for applications such as energy storage, polymerizing platform, drugs precursor, and biological markers. Um, and well, the summation of all these features made us turn our attention to this system. In particular, we were interested in studying electron rearrangements driving the pyrolytic transformation of Cubane. However, the chemical bond is not a physical observable, and this is why alternative approaches have been proposed to bypass this limitation. And among such methodologies is the so-called quantum chemical topology, which leverages the topographical analysis of the gradient vector field generated by scalar functions to extract valuable chemical information without explicitly mentioning the reference state. So this is basically a way of systemizing the work of Bader, who used the electron density to study the chemical bond and reactivity. And within this quantum chemical topology umbrella, there is a similar method known as the bonding evolution theory, or BET, that extract meaningful chemical information from the topological analysis of the electron localization function, which is this function over here, instead of using the electron density. So basically, BET models a reaction system as a gradient dynamical system featuring the ELF as the potential function, and then the critical points of this function are determined and classified as attractors, saddles, and repellers, with emphasis on attractors, as they are associated with Lewis concepts like lone pairs, covalent bonds, and core. And there is another relevant collection of points, which is the bifurcation set, These points are degenerate in the sense that the Hessian matrix of then yields 0. And we will dig a little bit more on this shortly. And finally, the changes in the number of attractors, which provide a topographical description of bond breaking forming processes, are associated with an unfolding. And well, throughout this method, the Poincaré-Hopf theorem needs to be fulfilled. So, in this way, key chemical transformations are characterized in terms of a set of well-defined functions. So now let's get into some details concerning the bifurcation set and unfoldings. When two critical points of L approach, their Hessian values decrease, and if they merge, the value of such matrix will then be 0. Surprisingly, the change in the function shape can be captured by a remarkable collection of parametric functions derived within Thom's catastrophe theory, which are these unfoldings. So basically, these unfoldings remove the degeneracy of the so-called germ by adding perturbation. So, for instance, this is the well-known cubic function. So looks like this, as we all know, and this function is classified as a germ because in its origin it has a degenerate critical point. So I mean, it has two critical points with the same value of the Hessian 0 in this case, or in other words, these 2 points are folded. So when a perturbative term is added to this function, look what happens. Yes, exactly. The folded points unfold. And this is paramount for what is about to come. By systematically adhering to the mathematical rigor underlying bet, we had previously observed that only 2 terms unfoldings, the fold and the cusp polynomial, are adequate to describe scission and formation of chemical bonds. The former involving only 2 critical points, while the cusp 3. And this is worth remembering. So based on accumulated computational evidence, we decided to test this hypothesis about the existence of a close relation between these 2 unfoldings and the symmetry of the electron density along key electron reorganizations. And we selected the pyrolytic transformation of Cubane because of its remarkable features. So in essence, a 2-step mechanism is proposed to explain the isomerization of Cubane to cut, and the calculation of this first elementary step was conducted using this level of theory. And despite its relative simplicity, the computed barrier only deviated about 4 and 9 kcal per mole for the smallest and largest basis set respectively, relative to experimental estimations, which means that these levels are adequate to characterize the topographical changes along the reactive coordinates, as illustrated in this scheme. So we monitored the value of the determinant of the Hessian along all key chemical events, and let us analyze, for instance, the bond scission between carbon C1 and C2, C4, C8, and C6, C5. So I would like now to recall that, for instance, this ELF attractor A1 give us a topographical representation for the covalent bond between atoms C4 and C8, and similar for A6 and A8. So this plot show that any of these three attractors exhibit any signs of degeneration, as their Hessian increases just before the associated bond breaks. Therefore, all these electronic reorganizations must be described in terms of the fold polynomial. And the exact same thing happens along the entire Cubane to Bot transformation. Now, for the second step, we used several levels to show once more the consistency of ELF topographical results when based on the Hessian analysis. And on top of that, all these methods estimate the barrier with good accuracy, ranging from 0 to only 6 kcal per mole, and showing their suitability. So in this case, let us focus on the double to single bond reductions. I mean the bonds C1, C4, C5, C8, and also let us have a closer look to the transannular ring opening C3, C7. So this plot over here shows the values of the Hessian at attractor A3 as the bond between C3 and C7 stretches. So we see that the Hessian decreases continuously until eventually A3 it splits into three new critical points, these two attractors and this saddle point. And thus the transannular ring opening must be rationalized through a cusp unfolding, because the ELF topography changes in three critical points, and on top of that A3 it is not a degenerate point. However, the situation depicted by this other graph is completely different, as the reactance in center C1 and C4 separates only the attractor A15, and the saddle S6 degenerate, and similar for the attractor A18 and the saddle S12. So this all means that A9 and A10 are not degenerate, and since only 2 points are involved in each reduction process, both needs to be described in terms of the fold polynomial. Right, so to further explore these outcomes, we made use of these bots functionalized species which were synthesized some decades ago. So I want to draw your attention at these 2 points. First, the electron symmetry of this structure along the transannular ring opening is preserved with respect to a plane perpendicular to the breaking bond. But in this other case, that symmetry is destroyed, and finally it has been recovered in this third scenario. So if we plot the Hessian for these three attractors, we'll see that for the case in which the symmetry is preserved, the corresponding attractor degenerates. So take a look at what happened with A and A2I, so these two curves. So this is what happens for these two cases, but this one, but for this other case, the reality is completely different. So in the highly symmetrical systems, this one and this other one, the attractors are pulled evenly by atoms C3 and C7, because actually these bonds are not polarized. And this is exactly what triggers the splitting of the attractor A and the attractor A2I. However, in the other scenario, the bond is indeed polarized, and thus the attractor is pulled stronger for one of the centers, C7 in this case. And thus, with all this in mind, we focused on systemizing these insights, and to that end, we investigated the electron rearrangements featuring key classes of chemical reactions like isomerizations and twos and pericyclics, including electrocyclics and cycloadditions. And also, we computed the bond polarity index at each reactive center before the change in the ELF's topography. So this allowed us to quantify the correlation between unfoldings and the density symmetry via this simple scale, which basically shows that high values of this index correlate with the fold, while low ones with the cusp. And well, this study facilitates concluding that there is an intimate correlation between electron density symmetry and unfoldings in such a way that high values of the bond polarity index correlate with the fold unfolding, while the low ones with the cusp. And based on this, a scale has been proposed. So the cusp is the adequate polynomial to describe breaking and forming processes of the chemical bond when a plane perpendicular to such bonds yields two equivalent molecular fragments. And since no special condition is required for the fold, it is anticipated this unfolding characterizes most electron rearrangements along reactive coordinates. And finally, this study revealed a new facet between topology and the energetics of matter's transformation. So that's it. Thank you for your time.